All right, if you've ever touched Python for data science, you know NumPy is just everything. But let's be real, there's that one thing that gets everyone, I mean from total beginners to seasoned pros, and that's wrestling with array shapes. So today, we're going to crack that code once and for all.
Ah, yes. Tell me this doesn't look familiar. This little value error. It's basically the villain of our story today, right? It just shows up completely uninvited, crashes your code, and leaves you just staring at the screen going, what?
And you're totally right to be confused. What does this even mean, and how do I fix it? It feels like NumPy is speaking in riddles. Well, in this explainer, we're going to be your translator. We'll show you exactly what it means and how to shut these errors down for good.
And you know what? The secret, the key to unlocking all of this, it all comes down to one single powerful idea, and that is shape.
Seriously, so many NumPy headaches boiled down to this shape problem. But here's the good news. Once you get the hang of manipulating shapes, you can basically bend any dataset to your will. You can prep it for any kind of analysis, any machine learning model you can think of. It's a superpower.
So let's dive in. Our first clue to solving this whole shape mystery is a really cool NumPy feature. It's kind of like a magic trick. It's called broadcasting.
Okay, so what is broadcasting? Well, it's basically a set of rules NumPy uses when it sees arrays with different shapes. Instead of just throwing its hands up and giving you an error, it tries to be smart about it. It kind of relaxes the rules, letting you work with arrays that don't match exactly. It virtually stretches the smaller array to fit the bigger one. And the really cool part? It does this without actually using up a bunch of memory to create a new, giant array. It's super efficient.
Let's look at the simplest case, something you've probably done 1,000 times. You take an array and you multiply it by a single number, a scalar. See how that number gets applied to every single element? That's broadcasting. NumPy just broadcasts that single value across the entire array. You've been using it all along.
Now for a more common real-world use case. Imagine you have a 2D matrix of data, and you want to scale it using a 1D vector. Look at this. NumPy is smart enough to see that the vector can be stretched or tiled across each row of the matrix to make the math work. This is a game changer for things like standardizing your data.
So how does it know when it can do this? It's not actually magic. It follows two really simple rules. First, it lines up the shapes and compares them from right to left. Second, for each pair of dimensions it compares, they're compatible if they're either the exact same number or if one of them is 1. So a 3-4 matrix and a 4 vector, the rightmost dimensions are both 4. They match. We're good to go. But what about our original problem? A 3 and a 4 array? Well, their only dimensions are 3 and 4. They're not equal and neither one is 1. That's why we get that error.
Okay, so broadcasting is great, but what happens when the shapes are just plain incompatible? Well, that's when we have to step in and take control. And we've got two main power tools for the job, reshaping and transposing.
Let's talk about reshape. I like to think of it as data origami. You're not changing the data itself, the numbers stay the same, you're just folding that same piece of paper into a different shape.
So let's say you start with this, a simple, flat 1D array with 12 elements. Its shape is just 12 comma. But now, watch this. With a simple reshape, we can turn that into a 3x4 matrix. It's the exact same 12 numbers, in the same order, but now they're organized into a 3x4 shape. See? The data's the same, only the structure is different.
And here's a little trick that I absolutely love, the -1 trick. If you know you want 3 rows, but you can't be bothered to do the math to figure out how many columns that means, just put -1. NumPy will do the calculation for you and automatically figure out it should be 4. It's so handy and makes your code way more flexible.
All right, our other main tool is transposing. You usually see it as just .t. And for a 2D array, it does exactly what you'd think. It flips the rows and columns. So a 3-4 array becomes a 4-3 array. This is super important for a lot of linear algebra and matrix math.
So why do we even care about all this? Why is this so important? Well, it often comes down to one really crucial task, feeding our data into a machine learning model. Because here's the thing, libraries like scikit-learn are picky. They expect your data to be in a very specific 2D shape, n samples, n features. The rows have to be your samples, and the columns have to be your features. Get that wrong, and nothing works.
But you know, sometimes you need to go the other way. You need to do the opposite of reshaping. Think about image data.
You might have a 2D grid of pixels, but your model needs a single long one-dimensional list of all those pixels. You need to flatten it.
Now, to do this, NumPy gives you two options that look almost identical: ravel and flatten. And this is a really important pro tip because there's a subtle but critical difference between them. It all comes down to something called a view versus a copy.
So here's the deal. Ravel is generally faster and more memory efficient because it gives you a view. Think of it as just another window into your original data. But, and this is a big but, if you change something in that view, you are also changing the original array. Flatten, on the other hand, always returns a brand new copy, is totally separate. You can mess with the copy all you want, and the original data is safe. So it's that classic trade-off, right? Ravel gives you speed, flatten gives you safety.
Okay, so let's do a quick summary of our shape-shifting toolkit. We've got reshape, which is like our data origami for changing dimensions. We've got transpose, or .t, for flipping the axes. And for flattening, we have ravel for a fast view, and flatten for a safe copy.
And really, that's the core of it. You now have the power to understand and fix those frustrating shape errors. You know how to bend and mold your data to prepare it for pretty much any analysis you can throw at it. So I guess the only question left is, now that you have these skills, what complex data problem are you going to solve first?